Hey, John here. Let's talk about combinational circuits, right? So the first thing you're going to see is a combinational circuit is just a schematic drawing version of an equation like this. Let's look at equations 41 here and equation 47 and convert those into circuits and then go from there. Now, remember that a circuit is made up of a drawing that includes one or more of these gate symbols. It's a graphic representation of the Boolean algebra. AND gates, NOT gates, OR gates. We'll see NAND gates and XOR gates and stuff like that. And we'll just combine these things together to create increasingly complex and useful circuits. All right, equation 41 is what? It was A bar or A ended with B. I guess I used capital letters here, but you get the gist. Okay, so this is the same thing due to operator precedence as this, right? Now, how do we do this in a circuit? Well, we've already seen an AND gate, so we just list down the letters. We say A, we have a B, all right? Now we have A ended with B, so we can easily just take A. I'm looking ahead a little bit here, so I'm going to put these two together like this. Put that in an AND gate. As you saw before, this is how the AND function works. Well, what about this other stuff? Well, this here is A ANDed with B, all right? And I need to take an OR gate, which looks like this, as you recall. And I need to OR that, which is from here, with this. Well, that's just the same thing. You put a dot there. You put a gate like that. This now is equation 41 in schematic form. So what do we know? The inputs on the gates, as I've drawn them here, they're always on the left. You could easily draw a gate going the other way, in which case it would go to the right. I tend to go left to right when I write my schematics when I can. Okay, so what do we know here? We hook the inputs up to the letters that represent, or the names or the symbols representing the inputs, right? If you have a bar over it, that's a NOT gate. The AND gate looks like this. The OR function, the OR gate looks like that. And there you have equation 41 drawn out in schematic form. Now, we did simplify equation 41 to 47, and that equation was this, what? A bar ORed with B. I'll stick to my incorrect capital letters here. What do we got then? Okay, so you have just simply A. You may need to make an A bar out of A. Then you have to have a B. That goes into an OR gate like this, right? Obviously, this would cost less money because each one of these gates is actual silicon hardware that has to be purchased. So this here wins on money. So what do we know so far? Each one of these operators turns into a gate when you draw up the circuit. There's an OR operator, OR gate, AND operator, AND gate. The bar over the A, that is also a gate. A bar, the NOT function, is also a gate. The operators have inputs, okay? So if you put parentheses around them, even if they're gratuitous, like that is in this particular case, because you would do the AND function before you would do the OR, it starts looking closer to what you end up with your combinational circuit here, okay? The input to this OR gate has two operands. It has the A bar, which is right here, and if you really want to, you can go ahead and label that right in your schematic, right on that line. We call that a wire, because it literally becomes a wire if you build this as a real circuit. It's a metal thing that connects to transistors or gates or chips or whatever, however you build it. And the names on these wires should reflect, what the signal is. You could also give it like a user definable name if it has some function or role. In this particular case, this is all purely abstract, so it's like stop or go or danger or help or something like that. If you were building a circuit that had to do with like a safety system or something like that, right? So you can label the wires however you want. Sometimes I'll put the the actual sub part of the equation in there to remember where it is, because these can get pretty hairy if you have a lot of gates, right? And that's really all there is to it. A combinational circuit is just simply, literally what the word means, is a combination of gates, all right? Now notice one other thing. When you draw up a combinational circuit, there is never a situation where a wire would come from the output of a gate and come back either directly or indirectly around in a loop like this. That is a different kind of circuit called a sequential circuit. In combinational circuits, there will never be a feedback loop. So no feedback, okay? No, you'll never see it, either a little one like this or a big one around like that. No, not allowed. That feedback loop is not allowed. That's what means you have a combinational circuit. Okay? So there's some rules that we can see here. At any time, the output depends strictly on the current combination of the input values. Now, because of this, we can't always express these things using an expression in Boolean algebra. Because we can always express them in Boolean algebra, we can also always express them using a truth table. And as we've already seen in our Boolean algebra discussion, these things can have any number of inputs and any number of outputs. All right, so let's do something useful. Let's add two numbers. This is actually what we call a half adder, okay? All right, so how does this thing work? First, let's remember what it means to add. If we draw a truth table for adding, I want to add two bits, A and B, and I'm going to get a carry and a sum. We already know that. All the combination of the inputs are like 1. Oops. Forgot 0. 1, 0, and 1, 1, okay? What happens when you add 0 plus 0? You get 0 and there is no carry. 0 plus 1 is 1 with no carry. 1 plus 0 is 1 with no carry. 1 plus 1 is 0 with a carry. Let's build a circuit that does this, okay? How do we do it? Well, we have our A and we have our B. What do we see going on over here? Now, we can make a huge quantum leap by observing this is the XOR, is it not? 0, 1, 1, 0, 0, 0, 1. Clearly, C is the AND, right? So we can say C equals A ANDed with B. I drew a capital A there. I'm getting out of whack here. That should be a lowercase a. Okay, sorry. All righty. What is the sum? Sum is clearly A XORed with B. All right, you can look at that up, review that in the binary algebra handout. So how do we do this in a circuit then? Well, we can just simply hook A and B up to the XOR gate and label that our sum. All right, and then we hook up A and B to an AND gate for our carry. All right, now, when you do this, we need to make sure that it's clear to everyone where these wires really go. And you'll notice I put a dot when these things connect, and when they cross each other like they do right here, there's no dot there. Those lines are not connected, okay? So this means A goes into the XOR gate, and it also goes to the AND gate down here. And B goes to the XOR gate, and B comes down here, all right? You can cross the wires all you want, but only when there's a dot does it matter, okay? This is the schematic of what we call a half adder. Now, like all good programmers, the first thing we're going to do to this is abstract it, okay? Now, once you start getting a lot of gates on a page, you start seeing things getting put into black boxes. So one of the things that we'll do here is create a box. We'll just write HA on there for half adder. And since everyone knows what a half adder is, we can put an A here, we can put a B here, and we can put a carry here, and we can put a sum here, all right? This equals that. All right, so we know how to add two 1-bit numbers with a half adder. Let's look and see how we can add 1 to a multi-bit binary number with a half adder, okay? Or in this case, multiple half adders, all right? That's why we abstracted it away. So what if we do this? Let's take a half adder, and hook it up like this. Take the A input, and we'll just call that D0 for now, all right? We'll see why in a minute. The B input, let's leave that sitting there without looking at that for a minute. Let's leave that one go. The sum here, let's call this S0, is the sum output. And here's the carry output. Now, what are we going to do with that? Well, remember, this circuit will add these two numbers together, put the sum here, put a carry here. We already know how to add, we know how to count and binary and stuff like that. Looks what happens if we do this, right? This carry needs to be added to the next digit in our number, right? So we take the carry, and we've just propagated over here. So here's my A input and my B input of another half adder. We'll call this one D1. Now, as you can see, D0, D1, we're building up a multi-bit binary number here that's going to flow in from the top down. The incremented value, we say, will flow out the bottom down here. When we want to add 1 to it, it'll come out these S0, S1, so on. So here's the sum for this one. Call that S1. The carry for this stage is going to go over, up, and around like this to another half adder. Sum will come out here, S2. Sum, carry. You see where I'm going with this, right? You can just keep on doing this forever if you want to. We'll have to look at some of these issues that will arise if you do that. Here's your B input and your A input here, and your B, your A. You almost don't even need to really label these at this point. D3, let's just stop here. The sum for bit number 3 will be here. What are you going to do with this thing? The carry here, we'll just call this the carry that goes along with our sum, right? If you have a 4-bit number, we can call that D0, D1, D2, D3. Those are the 4 bits. This is my input, right? All right. Down here, the 4-bit sum is expressed with these 4 bits, all right? And what are we going to do about this signal? What are these all about? Well, if I put a 0 on here, what's this half adder going to do? It's going to add D0, whatever it is, plus 0. Well, the truth table is sum will be whatever D0 is, right? If D0 is a 0, the sum will be 0 and the carry will be a 0. If D0 is a 1, the sum will be a 1 and the carry will be a 0. That's all there is to it. Adding something to 0 is going to yield whatever the something is, all right? And because this carry is a 0, this here will propagate through by adding 0 to whatever D1 is and give me D1 here with a 0 on its carry, and that'll propagate over to here, which will mean D2 plus 0, S2 will be whatever D2 is with 0 carry, and you get the picture. That'll go on forever, all right? So, what if it's not 0? What if it's a 1? Well, we know what a half adder does. If D0 is a 0, that'll be our simple case here, and we add 1 to it, the sum will be a 1, the carry will be 0. And then we have the same situation we had before. 0 plus D1 is D1, no, with the 0 for the carry, and that'll be D2 will flow through here with a 0 coming in here with a 0 with the carry and so on, right? Right? Because if, by definition, if D0 is 0, and I add 1 to whatever this multi-bit value is here, this sum will be a 1 when there will not be a carry. I mean, that's the definition of what's going on. If D1, on the other hand, is a 1, and we have this B input set to a 1 over here, now we have an interesting situation, all right? Because 1 plus 1 is 0 with a carry. Now, whatever D1 is will get added to this 1 here. And either, if D1 is a 1, then we end up with a 0 and a carry again, right? So eventually, if one of these inputs turns out to be a 0, that carry would get consumed and propagated out in the sum here. right? And then there would be a 0 and a carry. The rest of the number would be okay. So if we look at this in binary, we'll see whenever you're adding 1 to a binary number, it'll create a ripple effect on all the carries for all the least significant bits that are 1s until it gets to a 0. Okay? I'll leave that as a test to the viewer to work that out. If the input here is a 0, the inputs will be left completely unchanged, as I said earlier. So what other interesting things can we observe about this, right? Well, this carry chain will go on forever for as many bits as we have in here. So whenever you add 1 to something, it could cause a ripple through this entire carry chain. This is called a ripple adder, by the way, because of this rippling effect, all right? Now, it's going to take time, is my point, right? So what do we know? What can we observe? Nothing in the universe is infinite in speed, right? We always have the speed of light problem, right? So the carry chain will take time to propagate through all of these half adders, is the point, all right? The longer it is, the longer it's going to take to add 1 to it. Now, how would you describe this, right? How would you draw a truth table for such a thing? Well, you've got 1, 2, 3, 4, 5 inputs, really, if you even count this, all right? What would you call this, by the way? I would call that carry in, okay? This one over here would be just the carry, or you could call it carry out, okay? Why? Because this is the least significant bit coming in. They carry into this adding operation. And this is the carry coming out of it. Because we know that if all the inputs here are 1s, this would be, if it was an unsigned binary number, that would represent 15, right? In decimal, or F in hex, right? If you add 1 to F in hex, you get 1, 0 in hex, right? Well, that means 1, 1, 1, 1 plus 1 would be 0, 0, 0, 0 with a carry. All right? So how would you draw up this truth table? Well, let's take a look at that. I would do it like this. You could do this in many different ways. If you wanted, you could just simply show 16 rows, right? You have 4 inputs. You could just assume the carry input is always a 1. If you wanted to show the carry input, then there would be, what, 32 rows, right? So let's go ahead and abbreviate this truth table. So I would say we have D3 through D0, okay? And we would have carry in as our inputs in our truth table, okay? Our outputs, I would say we have S3 through S0, and that's just one column I'm going to show you in a second. And we have a carry out. All right. Now, I'm going to just say I don't care what D0 through D3 is. I'm going to just call that N. Right? Again, we're abstracting things away to make it easier to read this thing. If carry in is a 0, we know that whatever D3 down to D0 is, this 4-bit number is going to come out this sum. Because n plus 0 is n with 0 as a carry out. That's what we're going to get. Okay? Now I can say n with a carry input of 1. The sum would be n plus 1. Right? And what would carry out then be? We could represent this any one of a number of ways. We all know how to write C and C++ programs. And most engineers know how to write Verilog that would be looking at a set of code like this, or, you know, VHDL or something like that. And they all support the same kind of a thing. You can say this, n equal to 0x f. Well, actually, double equals. I don't make a dumb mistake, right? You need to compare n to f. Question mark. If it does equal f, then it will be a 1. Otherwise, it'll be a 0. Okay? You can code this in a C program. You can code that in a Verilog program. This is a generally acceptable way to express this. And if it's not as general as I say, it will be in this lecture. Okay? All right. So we have a very simple truth table. This table represents the inputs and the outputs of an incrementer, a thing that takes a 4-bit binary number and increments it by 1. It adds 1 to that 4-bit number, and this is the truth table for that. Let's take a quick glance back at the half adder truth table, okay? We have two 1-bit inputs. We have a carry and a sum output, all right? What then is the other kind of adder? So if that's a half adder, is there a whole adder? Well, no. Well, yes and no, although it's not called a whole one. It's called a full adder. Now let's start by looking at what the truth table looks like for that thing. What we're going to look at in a full adder is we're going to have an A input and a B input, just like before. But we're also going to have a carry input. Okay? Then we're going to have a sum and a carry output. You know what? When I draw these, I like to have the carry output on the left. How then is all this going to work? Well, we have 3 inputs, so how many rows are going to be in this truth table? There better be 8, right? And if you can't count in binary, you cheat and go like this. You know, this is your 1s, 2s, and 4s, so that's going to be 4 zeros followed by 4 1s. All right, what's this? Your 2s, double O, double 1, double O, double 1, like this. And this is your 1, so you got O, 1, O, 1, O, 1, O, 1. This is counting from 0 to 7 in binary for 8 values, okay? Now, what is the output of this thing? Now, we already know what this is because we were doing a bunch of adds earlier when you're just adding 2 binary numbers. So let's calculate it out. Now we're adding the 3, right? Because we're dealing with propagating a carry through an addition, all right? So 0 plus 0 plus 0 is 0, and there's no carry. 0, 0, 1 is what? 1 with no carry. 0, 1, 0 is a 1 with no carry. A 0, 1, 1 is a 0 with a carry. That's a 1 with no carry. That's a 0 with a carry. That's a 0 with a carry. That is a 1 with a carry. Okay? Now, you can recognize that this column over here is the 3-input exclusive OR of the 3 inputs. And if you don't, let's take a quick look at it. Remember, the XOR means odd parity. So how many 1s are there? 0. 0 is an even number. Sum is 0. Odd number. Odd number. That's 2. Even number. Odd number. Even number. Even number. Odd number. So there's your sum. Sum is simply the XOR of the 3 input bits. Carry out. Well, that's a little bit more complicated. We could draw up a sum of products for this and then reduce it. But I'm going to leave that as a task for the viewer. Okay, I got to leave you guys something to do for homework. All right, here is the reduced form of what we call a full adder. This is a very standard circuit. You'll see it all over the internet. So you have an A input, you have a B input. Draw them going into an XOR gate like this. Okay, we draw that going into another XOR gate like this. This is our sum. Okay, put the carry input right here. Put that in there. So this is, as you can see, this is a 3-input XOR, right? It works just like the AND function and the OR function. You can cascade additional inputs by just adding gates like this. Here's a 2-input XOR. Oh, I want a 3-input one. Well, I'll just connect that to this other XOR over here and take my 3rd input like that, okay? Now, how do we do with this carry out stuff? Well, that's more complicated. Let's, once it's reduced, you're going to find out it looks like this. An OR gate here. Carry, put a little O for carry out. There'll be another AND gate down here. All right. This AND gate here is going to tap into here. And it's going to tap off of this. All right. The AND gate down here is going to tap off the A and the B inputs like so. All right. Now let's look at this circuit again. I already discussed the sum and how that you can just cascade these XORs together and kind of get that to come out. You can do the reduction in Boolean algebra, and you can find that this is one of the possible ways to implement this thing, okay? Especially for the carry. Look what's happening with the carry here. What is this? This is A XORed with B, right? That's what's coming out of that gate. And then we have the AND function here. All right, so let's just look at this for a second. What's this signal here? Well, this is A XORed B ANDed with carry in, all right? So we can kind of see what's going on here. A XOR B. Now, if we wanted to draw up an extra column in here just for discussion, let's just put it over here. A XORed with B, all right? We're going to add an extra column in here just for fun. What is that? Again, you're even in the odds, right? So this is 0, 0, 1, 1, 1, 1, 0, 0. Okay. This is A XORed with B in this column. So if I take that and I AND it with the carry in, let's look and see what's going on over here. Here's my carry out. Here's my carry in. All right. If I take these two columns here, right, just the two columns you're looking at, I'm going to have a 0 and a 0, and I'm going to have a 1 for this row here, right? Notice we got a carry out there. Then I got a 0 here, 0 there. I got a 1 here. I'm going to AND those two together, and I got a carry out that's a 1 there as well. Now, this is a 0 here, so I know I cannot output a 1 in these cases, right? Well, this AND gate is taking care of these two situations with this carry out is what it's doing. The other AND gate down here is true when A and B are both true. Look at this. Well, the other AND gate takes care of these two carry out cases, and because I OR that together, that's how carry out comes out. All right. So this is a reduced circuit. And you can actually kind of trace it through, and if you can't do it in your head, add more columns of this truth table, work this out, convince yourself that this is correct, because I know it is. All right. Now, how do we abstract this thing away, right? Well, same kind of thing we did with the half adder, but this time we're going to do a full adder. We draw a nice little black box, and we say, hey, it has an A input, and it has a B input, and it has a C sub I input. It has a sum coming out of it, and it has a CO coming out of it. All right, so there's our full adder in abstract form. Inside this box is that whole schematic right there. All right, so what do we want to do with a full adder? All right, well, same kind of thing we did with a half adder, really. Full adder, we're going to gang them together, and we're going to use them to add stuff, okay? Remember the half adder, what we could use it for is to add 1 to a multi-bit binary number. We just chain them all together, okay? Full adder, we can use it to add 2 multi-bit numbers together. So let's look and see how that would work, right? Let's call this one A0 and B0. Okay, that'll go to our A and our B inputs. The carry input over here, we'll leave that for a second. We'll come back to that later. Call this S0 for some bit number 0. Carry out, what is that one going to do? Well, that's going to be your chain again, right? Full adder. I mean, you should be able to see this now. We added binary numbers together earlier on. Carry in, A1, B1. So these are your zeros, your ones, you know, your ones, your twos, your fours, your eights, all right? The zeros and ones, these are the power of 2, right? So when we added numbers together in binary, we were adding the A and B inputs. These are your add-ends, all the A's and all your B's. The A's are one add-end. All the B's is your other add-end, okay? So you should be able to see what's going on here now. Carry out. Full adder. Sum 2. Carry out. Let's just make another 4-bit adder. For sake of completeness, carry in. Carry in. I forgot. Let's not lose track of counting here. B2, A2, B3, and A3, right? Your A input and your B input, your sum for 3, and then you have a carry out over here, okay? Just like when we're adding, you know, 4-bit binary numbers by hand, you always had to worry about this extra carry out over there. And remember, we used to play games with this carry in the far right column also sometimes, right? That had to do with subtracting. We'll come there and we'll get there soon enough. For now, let's just set it to 0, okay? So, what does this then mean? If that's a full adder and we're going to add A to B, get the sum of these, of these two bits come together and we get a sum and a carry, we can then add the next column of bits for A and B and the carry that propagated from the prior column. Get the output there and the carry, right? Add these two bits and its carry in and get the sum for the bit of this column, and this goes on forever. Now, just like the half adder, this is a ripple carry adder, right? And this ripple is going to deal with it's going to create a delay, all right? The sum and carry here will be calculated before this one will be calculated and so on, all right? Because it just takes time for the data to propagate all the way through here. And the length of this carry chain is proportional to how long it will take for this thing to do its job. So if you're going to add two 64-bit numbers together, you'll notice it takes twice as long than it will be to add two 32-bit numbers together. If you use a schematic like this, there's other ways to make adders that work faster. They're called look-ahead carry adders. You can Google this. I'll bet there's a look-ahead carry webpage in Wikipedia specifically on this topic. Now let's take the abstraction up one more notch, okay? Let's put together an adder. What is an adder then? An adder is a thing that adds two multi-bit binary numbers. So this abstraction, again, we're going to have a nice box. Abstract everything away, okay? And what are we going to do? We're going to have the A's, we're going to have the B's all coming in here, and we're going to have a carry in. Okay, we're going to have a sum coming out of it, and we're going to have a carry out coming out of it. All right. Now, I'm not going to draw all the A's and all the B's and all the sums. All right. What I'm going to do, I'm going to add another word to our vocabulary now. Bus. Okay. This is the A bus, the B bus, and the S bus. What is this thing? The definition of bus is a collection of related signals. Now, very often you hear people refer to data buses and things like that. Well, the A bus, the B bus, and the S buses are all data buses. All right? Now, if this was an adder that had 4 bits for A, 4 bits for B, and 4 bits for S, this would be a 4-bit adder. All right? The A bus has different notations. Sometimes you'll see me, I'll mix these. It depends if I'm writing by hand or using a CAD tool. There's a couple of different standard notations. Like maybe if this was a 4-bit adder, we have A0 through A3 for those 4 bits. That's your A bus. Another way to represent the exact same thing might be A sub 0-3. Okay. Another way to do it would be A open square bracket 0.3. All right, I don't do this when I'm writing it out by hand. This is a very common notation that's used in a CAD package that I use when I draw up schematics and stuff like that. So if you Google around on the internet and you're looking for circuits, you'll see all 3 of these notations and possibly even more. Sometimes you might see a colon instead of the 2 dots, or maybe they'll reverse the order of these numbers. It seems there's no shortage of ways to represent this, but just so you understand, okay? This is a data bus, right? And maybe I'll say 0-3, B0-3. I'm sorry, I didn't leave enough margin here in this particular drawing as 0-3, all right? Just to drive home the fact that these are buses, all right? When you're using a CAD package to draw these diagrams, quite often when you draw a line that represents a bus, it will draw it in a different color, or it'll draw it like super thick like this, all right? So sometimes you'll see lines that look differently if it's a bus with multiple signals in it, all right? So you might end up looking like that. One closing thought on the way out of the door here. What do you think it would be like to try and express the carry out using Boolean algebra for just this 4-bit adder? What do you think it would be like to express it on a 64-bit adder? Think of the number of variables and operators in that expression, because it obviously involves the carry in and the 64A bus values, the 64B bus values, and this 64, all those carry. Oh my gosh. So think about that, and now think about the drawing you're looking at, right? This is why we don't use Boolean algebra to express more complex circuits. We want to abstract as much away as possible while still retaining an understanding of what the circuit really does. So thanks for watching. See you next time.